I'm Sigal, and I'm going to tell you today about optimal stopping with behavioral biased agents. And this is a joint work with John Kleinberg and Bobby Kleinberg. We need to make decisions all the time. Traditional economics assumes that in making those decisions, we behave rationally and make them simply to maximize our utility. However, behavioral economics observes that in practice, our decisions are often suboptimal. And one reason for this is that they are influenced by irrelevant factors. For example, empirical evidence shows that investors tend to avoid selling stocks below the purchase price. Now, this is clearly irrational behavior. What does the purchase price has to do with the decision on whether to sell the stocks or not? This behavior can be explained by the following two biases by Kahneman and Tversky. So first of all, we have reference points. And this means that gains and losses are computed with respect to some reference point, so some notion of status quo. And in the stock example, this is the purchase price. Second, we have loss aversion. So losses are way higher than gains. People care more about losses than gains of the same magnitude. And putting these two together, we get that people tend to avoid outcomes in which they experience a loss relative to the reference point. In this simple example, the reference point was fixed, so just the purchase price. But is it necessarily the case? In fact, in more complex scenarios, the reference point may change over time. And this was demonstrated by an experiment that Schunk and Winter ran. Roughly speaking, in this experiment, subjects has the following search task. So they had to buy some item, and they need to visit stores to find this item at the lowest price. And at any time, they could stop and buy the item. And what Schunk and Winter showed that the subject stops searching prematurely, and that the search behavior was consistent with a changing reference point, where the changing reference point was the minimal price that they observed. This experimental setup is very similar to optimal stopping problems. So those are problems that have the following structure, and we are thinking about a hiring problem. So we have n candidates, and the values of the candidates are drawn from a known distribution. So each candidate may have its own distribution, and we need to pick one of the candidates. Now, there is an agent that is interviewing the candidates one by one, and once a candidate is interviewed, then its value is realized. After the value was realized, the agent needs to decide whether to hire the candidate or not. And all hiring decisions are final. And the objective is to hire the best candidate. The celebrated profit inequality tells us that there is a stopping rule that selects a candidate with expected value, which is at least half of the best candidate in hindsight. Now, as we mentioned, this setup is very similar to the experiment of Schunk and Winter, and we could ask ourselves, what happens if the agent at making these decisions is biased? So we consider a reference-dependent agent that has loss aversion. We model this agent by first a parameter of lambda, which is greater than 0, and this is a parameter denoting the extent of the loss aversion. So lambda equals 0 is an unbiased agent, and as larger as lambda, the higher is the extent of loss aversion. And the changing reference point is going to be the value of the best candidate that was interviewed so far. So we're going to update this reference point as the agent is interviewing more and more candidates. So let's denote this value by V. And now, if the agent ends up hiring a candidate of value U, which is less than V, then we are going to assume that he's going to exhibit some loss with respect to the best candidate he already interviewed. So his utility is going to be V, the value of the candidate that he hired, minus lambda multiplied by the difference between the candidate that he could have hired, so the best candidate that he hired so far, and the candidate that he actually hired. Yeah, so this captures its regret or loss for not hiring the candidate with value V earlier on. And we assume that the agent is sophisticated about this bias. So this means that he knows that he will exhibit some loss if he ends up hiring a candidate which its value is lower than the value of the candidate that it's already interviewed. So this means that the agent is going to choose a stopping rule in order to maximize its expected utility. Let's see an example to clarify the model. In this example, we have two candidates. So the first candidate has a fixed value of half, and the second candidate has a value of 4 with probability quarter and a value of 0 with probability 3/4. So in this instance, the expected value of a profit is expected value of the best candidate. The best candidate is it's 3/4 with probability 3/4 half and with probability quarter 4. So this is the expected value of a profit. If you consider an unbiased agent, then an unbiased agent is always going to hire the second candidate, since its expected value is 1, which is higher than the value of half of the candidate 1. And now let's think about lambda bias agents. So in general, the optimal stopping rule for lambda bias agent could be computed in polynomial time, since this is a Markov decision process. Let's see what would a two-bias agent do in this example. So again, if he hires the first candidate, then he has expected utility and value of half. But if he hires the candidate 2, then its expected utility is going to be this. So first, the expected value of the candidate is 1. And then the agent is going to exhibit a loss in case that the realized value of candidate 2 is only 0. So the second term here is the loss that he's going to exhibit. And since the expected utility for hiring candidate 2 is quarter and the expected utility for hiring candidate 1 is half, then the lambda, a two-bias agent is going to always hire the first candidate and has expected value of half. And this example illustrates the problem of the bias agent. So similar to the experiments, since the agent really fears of losing, then it stops charging prematurely. And it is interesting to compare how much it loses because of this behavior. In this specific example, we get these bounds. And our first set of results provide general bounds on this performance ratio. We begin with the profit inequality type of result. Now, throughout the rest of this talk, we are going to denote by V star the value of the best candidate in hindsight, and V lambda random variable equals to the value of the candidate chosen by an optimal lambda bias stopping rule. Now, recall that this lambda biased optimal stopping rule is the one that aiming to maximize the agent's expected utility. So what we show is that the ratio between the expected value of the profit and the expected value of the lambda biased agent is bounded by lambda plus 2, and this is tight. The example showing the tightness is very similar to the example we've seen in the previous slide. So the value of the first candidate is fixed, and the value of the second candidate is very high with very small probability and is otherwise 0. So the bias agent is always going to hire the first candidate, and this is going to get us the gap of lambda plus 2. For the upper bound, we build on Samuel Kahn's proof for unbiased agents. So instead of analyzing the optimal stopping rule, we show that the suboptimal stopping rule, which is easier to analyze, already achieves the desired bound. And the stopping rule that we analyze here hires the first candidate with value greater than theta, where theta is chosen such that the probability that the value of the best candidate is greater than theta equals lambda plus 1 over lambda plus 2. Now, another interesting comparison, which is kind of more unique to our model, is between the value of an unbiased agent and the value of a lambda biased agent. And we show that this ratio is bounded by lambda plus 1, and this is also a tight bound. So before proceeding to give you the idea of the proof, we'll need some notation. So we denote by pi lambda the optimal stopping rule for a lambda biased agent, and by pi 0 the optimal stopping rule for an unbiased agent. And similar as before, we define these random variables. So the first thing we do is use pi o in order to get a lower bound on the expected utility of the bias agent. So the bias agent could always use pi o. And in this case, its expected utility would be, first, it's composed of the expected value of the higher candidate, and this is just the expected value of V0. And the expected loss is at most expectation of V star minus V0. So this will be the loss only for the cases in which the optimal strategy missed hiring the best candidate. So putting this together, we have this lower bound on the expected utility of the biased agent. The second thing we're going to do is we're going to look at the bounds that we already proved. So we denote by beta the bound between profit and biased agent, and delta the bound between profit and unbiased agent. And with this notation, the bound that we are looking for, what we want to get an upper bound on, is beta over delta. So again, let's go back to the expected utility of the biased agent. So we have the lower bound. Here we just did some rearranging. And we also have an upper bound of the expected value of the hired candidate, since the expected utility is simply the expected value minus, possibly minus some loss. Now, if we take these two and do some rearranging, we can get an upper bound on beta in terms of delta and lambda. And we also have another upper bound. We know that beta is at most lambda plus 2. This is what we proved in the previous slide. So putting these together, we have that beta over delta is at most the minimum between these two ratios. And we want to maximize this upper bound, so it is maximized when they're equal. And in this case, we get a bound of lambda plus 1, as we wanted. The following table summarizes the results we have regarding the homotonicity of the expected utility and value as a function of different parameters. So as the reference value increases, the expected utility may only decrease. And one reason for this is that simply the magnitude of loss is increasing. Now, one might suspect that another reason is that the agent would tend to hire candidates earlier in the order, and this will cause the expected value of the candidate hired also to decrease. In fact, it is not necessarily the case, and in some instances, the reference value increases, and the expected value of the candidate is actually increasing. As lambda is increasing, both the expected utility and the expected value of the candidate are both decreasing. And roughly speaking, the reason for this is that the agent indeed tends to hire candidates earlier in the order. And what we do is formalize this notion of hiring candidates too early and show that as a result, the expected value of the hired candidate can only decrease. Another parameter that we consider is the number of candidates. So for unbiased agents, as the number of candidates increases, the expected value may only increase because one can simply ignore the new candidates. Here, the answer is the behavior depends on where we place the new candidates. So if the new candidates are placed at the end of the sequence, then it's still the case that adding more candidates may only help and increase the expected utility and expected value. However, if those candidates are placed at the beginning of the sequence, then the expected utility may either go up or down, and the same thing goes for the value of the candidate. When the expected utility and value goes down, then they go down by a factor of at most lambda plus 1. As we just saw, the ordering of the candidates can affect the agent's expected value. So this motivates us to consider some ordering problems that were studied in the literature. First, we consider the case in which candidates are ordered uniformly at random. So now expectations are taking both over the orderings and over the values of the candidates. So we show that in this case, the ratio between a profit and the lambda bias agent is at most n, and this is a tight bound. For the upper bound, we consider the strategy of always accepting the first candidate, and our lower bound, the construction requires lambda to be quite large, so it needs to be exponential in n. And in fact, as we show, this dependency is required, since we also get a bound of log lambda, and this bound is also essentially tight. Now, the later bound is exponential improvement over the bound of lambda plus 2 we previously had. And in this, for the proof, we use a threshold strategy. And for lambda greater than 0, we actually get a new proof for the bound of E over E minus 1 for profit inequality. Another type of ordering problem we consider is one in which the agent or someone else may choose the ordering before in order to maximize the expected value. So again, we first have a bound of n, and the bound of n from previously carries over, the lower bound carries over since the construction we have is a construction in which all the candidates, the values of all the candidates are drawn from the exact same distribution. Now, this distribution has 3 values in the support, and we show that this is crucial for having a lower bound of n, since when we consider distributions that have only 2 values in the support, we show a bound of 2 on this ratio. And this is another exponential improvement here. So let me briefly sketch our proof for the bound of 2. The proof has a similar structure to Agarwal et al.'s proof of 5 over 4 bound for unbiased agents. So we assume that the value of agent I is high with probability pi and is low with probability 1 minus pi. And we show that the best of the following 2 orders gives expected value of at least expectation of p star over 2. So we pick here a special candidate. This is X sharp, and this is the candidate with the maximal low value. What is special about this candidate is that we are going to hire a candidate prior to it in the order only in case a high value is realized. So now we consider the 2 orderings. The first one, we simply order the candidates in the crossing order of their high value. So the blue candidate here is X sharp. And the second is we slightly modify this ordering and push the blue candidate X sharp to the right and put all the candidates such that age I is greater than its expected value prior to it. Now, if the value of the best candidate is prior to X sharp, then this candidate would be hired in both orderings. If the value of the best candidate is H sharp, then it would be hired in the first ordering. And if the value of the best candidate is in the interval between the expectation of X sharp and H sharp, it will be hired in the second ordering. And because of this, what we are able to show that the sum of expected values of the candidates hired in these 2 orderings is at least the expectation of V star, which would give us an approximation of 2. Let me summarize. We saw that results in well-studied models substantially change when assuming that decisions are made by biased humans. In particular, we presented a behavioral motivated model for optimal stopping problems, taking changes in reference points into account. And we saw that loss in performance is increasing with lambda, both with respect to a prophet and to an unbiased agent. Now, there are exponential improvements if instead of considering a fixed ordering, we consider a random order, or we allow to pick the best order, and here we constrain ourselves to 2-point distributions. Let me mention some open questions. So first of all, find an algorithm for computing the best ordering for 2-point distributions. And second, in this work, we made the assumption that the loss aversion is linear in the loss. Now, it will be interesting to consider other functional forms of loss aversion and see how do they affect the results in the model. So that's all. Thank you.